Thank you for the introduction. So this presentation is going to be a bit reminiscent with the previous one. We'll be focusing a bit more on implementation specifics. So I'll be giving a presentation about our first in-orbit demonstration of the SATlink product, which we have been developing for a year now. And I will also be taking this opportunity to give you a glimpse into how we integrate our solution into the ground and space segments of the new space industry. So before we go further, I need to give you a bit of context because SATlink is a software product that is mainly concerned with satellite communications. So let's paint a picture of the land here that you have probably seen 1,000 times today, but let's be on the same good terms. So satellite communication is a complex infrastructure. It can involve multiple satellites in orbit in constellation, which communicate with multiple ground segments, stations, which are connected to tracking, telemetry, and control servers, and which are used by operators to control and monitor their satellite. So nowadays, one of the pain points we can observe is that a lot of these infrastructures are implemented as, well, with no kind of data security attached to it. So it's all done in clear mode. There's no authentication, there's nothing. So people who can interject themselves, so we're talking about people who have access to basic radiometer equipment, knowledge of standards, they can present a threat. Well, there are two main issues. First of all data that you generate on board your satellite is not guaranteed to be confidential. Second, the satellite has no way of verifying that commands that you send to the satellite or information is coming from its rightful operator. This is why we have developed SATlink, which is a product that we deploy both on space and on the ground to provide end-to-end protection to all the data transiting between two endpoints. So this is a product which is which is implementing the CCSDS SDLS standard. So we've had a few talks about this today, and you've maybe been to the workshop this morning, which was very interesting. And this implementation gives us the authentication and confidentiality guarantees that we need to protect the data. This is something that I presented extensively at CYSAT last year. I will not be giving the same presentation. I will be going to the next step of this process, of the development of SATlink, and I'll be talking a bit more about how we integrate SATlink with the ground and space segments of future space missions. So to that effect, we're going to go through the following points. Sorry, too fast. First of all, I'll be giving you a brief overview, I promise, of space SATlink security. I will not go into too much detail, but just so you understand what's going on. I will then tell you about how we deploy our various variants of SATlink, after which I will tell you about how we make sure the integration process goes smoothly and we are not, let's say, breaking the satellite communication. And finally, I'll be giving you a glimpse into our first in-orbit demonstration, so I'll be skipping a few steps into the future of that integration process and give you the first results we've had in orbit with our product. So, SDLS. So, you know the drill by now. It's a data link security protocol published by CCSDS, which aims to secure communication. It reposes on symmetric cryptography, and the way it works is we have frames which carry packets which are to be transported to a satellite subsystems or services. And they usually have this format where we have a header and a trailer, and more importantly, a data field containing all those packets. SDLS acts upon this frame by operating several modifications. First, we encrypt the data field, which contains all the packets, so that all data is obfuscated and not accessible to anyone who intercepts the frame. And second, we are also applying additional data in the form of a header and a trailer, which provide information such as a message authentication code. So this is the mechanism that allows us to ensure that we have authentication of the frame, because this can only be calculated by anyone who has the same shared secret as you. So this provides the authenticity, confidentiality, and integrity guarantees in the cryptographic sense that we require for the security of the data link. And there are additional mechanisms into the standard which allow us to avoid replay attacks. So this is to make sure that any command that has been accepted at least once by the spacecraft will not be accepted once more. So SDLS works with channels. You have multiple channels between two endpoints, which we call secure channels. And they are all configured by what we call security associations, or what I'm going to say is SA for short, because security association is a pain to say all the time. So these assays exist on each endpoint for each channel that you are securing. Also, each channel has the same assay, which is synchronized between the two endpoints. This data construct is sort of like a configuration like you would have for your VPN, and it contains important information about the secure channel. So for instance, we know with the assay which type of algorithm is used on a channel, which key is used to be for the encryption and decryption of the channel. And it also contains information for the receiver to understand how to interpret the security headers and trailers that are packed on the frame. Additionally, it keeps track of additional data, which is live and that evolves throughout the lifetime of the secure channel. For instance, the initialization vector when it's incremental, the sequence number, the current state of the security association, this type of thing. SDLS is a service-oriented protocol. So we have multiple services where we have, for instance, the baseline standard, which has a core service with two procedures, apply security and process security. This is the bread and butter of the security features of the SDLS protocol, which allow us to respectively encrypt and decrypt frames and calculate the authentication codes of frames that are transiting through the protocol. It's important to realize that these services rely on the manipulation of databases, so persistent data. We have security association databases and key databases, which are used by these procedures. SDLS is complemented by a series of extended procedures. So this is an optional extension of the standard, which provides us with management capabilities of the secure channel. And we have three more services which are grafted onto this. So we have an assay management service, which allows us to directly control the ASI database. This provides functions to start and stop security associations, to rekey them, to delete them. Then we have a key management service, which allows us to interact with the key database of an endpoint. When we have operations to do over-the-air rekeying, so upload a new set of keys to a satellite, we can destroy keys, we can verify if they're still valid, and this sort of operation. And finally, we have a monitoring and control service, which allows us to make sure that everything is going well with the secure channel. So that was for the very brief overview of the SDLS standard. I'll be going back a bit to SATLink. So as I mentioned, SATLink is a hybrid product. So I said we deploy it both in space and on the ground. What you need to realize is that it's not the same piece of software that we are deploying on both endpoints. SATLink is actually two products. We are developing SATLink Ground using the Rust programming language. It is made to be deployed on the ground, obviously, as the name implies. And it's made to be scalable and manage multiple satellites. It's usually developed as a master in the relationship between satellite and spacecraft. So for extended procedure, it will be mainly the initiator of procedures. Second, we have SATLink Space. So a bit different, it's developed in C, following ECSS software development for safety critical development guidelines. And it's much more lightweight. So basically, it's something that is bare metal. We can deploy on any type of architecture as long as we have access to the compilation toolchains. It's made to be very configurable. So we have observed that a lot of software and hardware environments of our clients are different. So it's important. And it's the main receiver of SDLS extended procedures. So now, in terms of deployment, how does that go? So SATLink Ground is inserted into the ground segment. The way it works usually is in an oversimplified manner. We have frames being routed from the mission control system all the way to the ground station, which relays packets over radio frequency waves to the satellite. SATLink Ground is inserted within that channel, where we have a queue that is used to process frames. So it is deployed either as a service on a cloud service provider. So we're currently supporting Amazon Web Services, AWS, or as on-premise deployments for the customer to do for himself. The SATLink service has a queue, two queues actually, one for apply security and one for process security, which are first in, first out, and which the client uses to push frames through SATLink to encrypt and decrypt frame both ways. We are also featuring a management services API. So this is used by the customer to configure and control the SATLink instance, but also to initiate SDLS extend procedures. So all the services I mentioned earlier, they're initiated by the user through this interface. This creates a set of extended procedure packets that have to be relayed to the satellite by the customer, which you can see here in blue. Now, on the space side of things, so this is going to be a gross oversimplification of how things go, but it's a good approximation. Usually, we have a communication subsystems, which handles all the radio frequency stuff for us. So modulation, demodulation, encoding, decoding, etc. And this goes on to either as a flight software implementation or FPGA, a routine that handles TMTC generation and decapsulation. Packets are extracted from the frame or inserted into the frame. This is then routed to the rest of the satellite. In this case, SatLink Space is implemented as a software library that you compile along with the TMTC and link routine, and which exposes an API that allows you to access all of the SDLS extend procedures. So apply security, process security, all the security association management service procedures, and all that. So this way it works is basically we have the flow of frames just going through the software using the library. So if we zoom out for a second, when we look at it, this is what's it looking like. And we can see that everything that's transiting between one SatLink point, which is ground deployment, and the other SatLink point is encrypted. Now, I'm going to talk more about how we integrate all this in real situations into a satellite and a customer's system. And the way it works is, well, ideally, in the best of worlds, we're just deploying SatLink ground on one side, SatLink space on the other side, and everything is good. But even in this case, we want to make sure things go well. But in some cases, some clients will have their own implementation for one side or the other, or maybe using proprietary solutions which already have an SDLS implementation. So it's going to look more like this, and we want to make sure that in any case, when we're integrating, we're always going to be compatible. So we developed a test environment which always tests one endpoint A on the space side, one endpoint B on the ground side, and make sure that everything is going well. So we assert several things. First of all, we make sure that two chosen SDLS endpoints, endpoint A and B, are compatible and can communicate with each other. So we have no problem with encryption, decryption, and this sort of thing. Additionally, and more importantly, we want to make sure that the secure link cannot be lost due to any, let's say, edge cases, failures that would happen with the communication or misuse of SatLink. This is very important to us. And third, also very important in the security standpoint, we want to make sure that we are resilient to any potential attacks that we can identify. So the way we approached this was develop an end-to-end testing simulation, where we have a software component which would drive all the tests. This software component has several systems. First of all, it consists of a test library in Python, which has several roles. It is responsible for building, executing the two endpoints we're going to test with one another. It's also responsible for running the tests with these endpoints and the given test scenarios that we provided. And it's also able to inspect and manipulate databases. So as you remember, we have for each implementation a security association and a key database. And each endpoint have their own persisting database that we have to look into. It's important for us to inspect these because we want to have the possibility to make assertions. For instance, if we send a new key to the endpoint, we want to make sure it has been correctly registered by this endpoint. Also, in the manipulation side of things, we also want to make sure to simulate failure cases or attacks. So this is a good way for us to directly interfere with the database and see how the system reacts to this. We have an API which is used to control all of the components at the same time and orchestrate the whole test environment. And finally, we have a list of test descriptions or test cases, which go through all the scenarios that we have identified previously. So all of this is implemented using the robot framework, which is a test automation suite written in Python. Now, onto the environment. So it looks like something like this. Usually we have a pool of endpoints we want to test on one side, a pool of endpoints we'll be testing on the other side. We're always testing one endpoint with the other, not everyone at the same time. And the test driver, which I've described earlier, is inserted in between these two. It does all the things I did. So it drives every endpoint through the API. It controls every database and inspects the databases through this library. And we have an additional software component in the middle. So if you've come to my presentation last year where I've demonstrated this SDLS implementation, you might be familiar with this. So we have a link proxy, which is inserted between the two endpoints, and through which all communications between the two endpoints transit. This link proxy has a frame manipulator component, which is responsible for two things. First of all, it allows us to simulate lossy communication or issues with communication with packet loss, packet deformation, this sort of thing. And additionally, it allows us also to simulate attacks. So replay attacks, tampering of frames, dropping frames, etc. All the kind of attacks that you would expect from a man-in-the-middle attack that were demonstrated in the previous presentation. Now, I'm going to skip ahead just before I go to that other step. I just want to mention that this test environment is something that we are using with our current prospects. We are currently integrating and testing our solution. And this is one way for us to make sure that every time we deploy with a customer, we are not breaking their satellite or their communication. So, as I said, I'm going to skip a bit ahead now. I'm going to talk about our first in-orbit demonstration. So, we've had the opportunity to fly on a satellite at the end of last year. So, the European Space Agency has approached us with the opportunity to fly on OPSAT. If any ESA representative is right here in the room with us right now, I want to reiterate our thanks for this opportunity because it was great to work with your engineers and it was a great opportunity. So we flew on OPSAT, which you may be aware of. It's a satellite that is essentially a laboratory in space and allows experimenters to deploy experiments, flight software experiments, or attitude control experiments, or this sort of thing, and make sure they can do these tests without having to develop a whole satellite and sending it into orbit, which is very costly. This, by the way, is the same satellite which was demonstrated to be hacked by Thales at the conference of CYSAT last year. So the way we approach this is as follows. We didn't do an end-to-end integration demonstration of Satlink space with communication in the ground. We wanted to extensively and acid test Satlink with a large amount of frames. So this was more of a contained experiment in orbit with Satlink using a large amount of frames. And we wanted to extract a few metrics from this experiment, of which there are two kinds. There are behavioral metrics to make sure that the Satlink implementation is behaving correctly. And there are also performance metrics where we want to make sure that we have good performance in terms of encryption, decryption, processing frames, and processing the security from the frame. So the way this works is we've extracted all of these metrics into a test plan, a complex test plan, which is described in several test description files. And all of this has been packaged into an experiment package, which features several tools, software that is run in orbit to generate a very high amount of frames. As I mentioned, we want to benchmark Satlink, so we cannot use up all the uplink the uplink budget we've been attributed. So this was one way for us to generate dynamically new experiments in orbit and have some randomness to it. So this was uplinked to the satellite, and we've been able to do a total of 66 runs in orbit. So this resulted in just under 5 million frames being encrypted and decrypted both ways. Which was a good amount of frames to process. And we've been able to do some verifications. So first of all, the encryption and decryption proceeded correctly. So we've been able to do this without any kind of issues arising. And more importantly, we've been able to verify that 100% of attacker frames, which are simulated in some test cases, have been correctly rejected by Satlink. Additionally, we have been able to verify a high repeatability of the measurements we've been doing on the performance. As you can see, we have a box plot here, and we can see the spread is quite thin. We do have some outliers, but in general, the data was very consistent. So in terms of performance, for a full software implementation, we've been able to verify a data rate of 5.2 megabytes per second both ways. You have to keep in mind that this measurement is done on an Intel Cyclone 5 chip, and it's running on a Linux system with other experiments running at the same time, potentially, so you have this impact. However, we have this in mind. We are currently working internally on implementing some of the cryptographic processes on FPGA. So we will have an hybrid implementation with Satlink as a flight software solution, using an FPGA for the cryptographic procedures. So what this means is that through this process, we'd be able to speed up greatly the data throughput that we currently have. So I'm reaching my closing remarks. I see here the moderator agitating himself. So as a summary of everything I've said, Satlink Space is a hybrid solution. We have a product which is developed for space applications, a product which is developed for ground applications. And all of this is integrated in a complex test environment, which is used for us to make sure that we are not breaking anything when we're integrating Satlink, which we are resilient to potential loss of communication with the satellite and this sort of scenario. Finally, we've been able to go one step further and fly Satlink in orbit to make sure that everything is going as we expected. And this has been a wonderful opportunity for us to get our first flight heritage from this. So if you're interested in getting some head start with Satlink, as I mentioned, we currently have several prospects, but we're always open to collaborating. Feel free to reach out to us at our stand here in this conference. And also, if you're looking for an opportunity, know that we are still looking for a flight software engineer for our Toulouse offices. So if you are interested by this, you can reach out to me or my colleague Sarah in the back. So thank you for your attention, and I will leave the floor now for questions that might arise from this presentation.
Fantastic presentation, and we do have the first question from Kimberly King. Does over-the-air rekeying work on constellations? If so, would the constellation share the same key for each space vehicle? And also, does SAT-Link software on space vehicle able to be patched on orbit?
So this is a good series of questions. First of all, note that SDLS in its current state is not a peer-to-peer communication protocol. We have usually a master-slave relationship. So there is no case where rekeying on constellations would work without any kind of adaptation. We would have always need to have some master-slave relationship between each of the nodes on the constellation. However, the SDLS standard is currently being worked on to be expanded to this sort of communication, peer-to-peer communication, and will include, dynamic key exchanges in the future. So this is something that, since we are aligning with the standard, we will be supporting as soon as it's defined by the standard itself. Now, on to your second point, SAT-Link, well, since it's a self-contained, very minimalistic software that you compile with the flight software, if you have the capability of updating your flight software, you are capable of updating SAT-Link as well, along with it. Does that answer your question? Thank you.
Thank you very much. We have the next question here.
Hello. I was just curious, you made mention of the CPU utilization, but you didn't provide any numbers for that. What was kind of the impact that you noticed on the Cyclone 5?
So actually, it's pretty minimal. We do have a number for this, but 20 minutes is a short duration for a presentation, so I could not show everything. However, I can tell you that with the experiment running and some other experiments in the background, we were able to measure the average load of the CPU over 5 minutes, and it usually never exceeded 2%. So you have to know that the benchmarks are done over 1,000 frames, but the process was always completed very quickly. So there's more time to set up the experiment where we load all of the frames in memory and then we process them. I mean, then the time it takes to process them. That's why you will never see a very high CPU load. Of course, during the short amount of time it takes to process the frames, you would expect to see 100% CPU load because you're doing this full bore without any type of preemption.
And just to confirm, that's the dual-core Cyclone 5?
That is exact. It's the Cortex A9 Cyclone 5 with an FPGA integrated in the SoC.
Thank you.
Okay, we have a lot of questions this time, which is great. Let's start here.
Yes, just a question with regards to the integration and deployment that you are planning to do with OPSAT. Does it mean that regarding the first figure you had, you will not test the inter-satellite link? You will have only one satellite and one ground level, or you will be able to test also? So
to clarify things, as I mentioned, the OPSAT deployment was not an end-to-end test. We do not have two endpoints communicating with each other. It's only one endpoint in a self-contained experiment in orbit through which we throw frames that we generate. Okay. But in essence, our deployment and the current ones we're doing with prospects is basically an end-to-end implementation where we have SAT-Link space on one side and SAT-Link ground on the other. With
security association from the ground to the final satellites you are targeting, or from ground to the first satellite and then re-encoding TCTM between satellites?
I'm not sure I understand your question. Are you asking about the provisioning of security association?
You are encrypting TCs and decrypting TM. My point is that when you're encrypting TC, which goes to a satellite in a rebound, like it was simulated, does it mean that the intermediate satellite is only a router?
Okay, there are no intermediate satellites here in this situation. We're really talking end-to-end between a satellite and the ground station.
Okay.
But so in the case of a constellation, what you would have is multiple secure channels between the satellite and satellite, satellite and ground. And in this case, the frame will be encrypted in the separate secure channels as they transit through the satellite, the relay satellite. So
Okay.
you would have different channels going on.
Okay, I was just confused by the first figure, but that's okay. Thank you for your answer
Sorry.
and your presentation. No, but that's fine.
If you're
Thank
looking
you.
for any clarification,
No, I
I'm
will
open
do.
to questions
No,
in my
fine.
booth.
I will be fine. Thank you very much.
The question about how do you protect the keys in your software implementation?
That is a very good question. So, first of all, you need to know that our implementation is modular. It's not just a monolithic implementation. We are we implement multiple backends. So the key storage can be done through a key management service, a KMS, through a TPM, etc. And we can interface any of these hardware or software components under SatLink. So the keys usually would be stored in an encrypted manner by the localized TPM implementation. And that is valid for both endpoints, so ground and space. It all depends on the needs of the customer and at which length they want to go to secure their whole communication.
Hello. Do you currently plan to have an end-to-end test soon or anything?
Do you mean with something in orbit?
Yes, exactly.
Yes, that's a very good question as well. Yes, that's something we would like to achieve, and this is something that might arise from our current prospects that we're working with currently. So, but yeah, it's something we want to achieve as soon as possible.
Do you test, like, I guess, on Earth already?
So yeah, of course, the integration environment I've been describing, where we test two endpoints between each other, has this whole idea of testing end-to-end. So it goes further than what we've demonstrated in our demo last year at the conference. And we can do this with multiple endpoints. So it can be satellite ground, satellite space. I think you saw also in the diagram, there's the NASA cryptolib, which has been helpful for us at the beginning of our development as a source of truth to test against for the extended procedures. And yeah, basically all of the possible combinations of SatLink, SDLS, whatever you want endpoints are tested automatically through this test environment.
Okay, perfect. Thank you.
Just to jump quickly on his question, did you, for any of the tests, use actual RF, or did you simulate?
No, so it's purely an emulation environment where all of the packets or the frames are transited over TCP from one endpoint to the other.
Okay, and do you
So
plan on testing it with RF?
not
to
really,
see if
because
there's degradation and so on?
Sorry, I cut you in the middle of your
to
question.
to see if it degrades the result that you obtained and so on.
So yeah, that is a good question. But since we are residing solely on layer 2 and we do not implement RF communication for our customers, this is something they do themselves. They use our product as a, let's say, tool to enable their communication with security. We are not doing this type of simulation actually. We are aware of the cost it incurs on the communication in terms of data throughput, processing time, latency, and this sort of thing, but we don't test it directly.
Okay, additional questions?
Thank you. A small question. So what brings end-to-end in-orbit demonstration compared to do everything on the ground?
Basically, it's the show. You have added value in doing so because you are demonstrating an actual scenario, a live scenario where you're doing this. So you're doing, in essence, the same thing as you would on the ground, but you're showing it in a real situation, which has a bit more weight when you're talking to prospects and customers who are interested in your product. Because what's essential for them is to know that the product itself has already flown successfully. So that's my answer.
Maybe one question to the implementation. You gave us a hook about your cybersecurity features, but is there actually a third party who evaluates the implementation of your cybersecurity solutions?
Do I understand correctly in that you're asking that there's a third party validating our implementation? Okay.
Yes. Certification or something like this?
No, there is no kind of certification regarding, as far as the SDLS standard goes, there's nothing because the CCSDS is not an authoritative body. It does not have any enforcement, let's say, power. But we do want to be compatible with the industry. This is why we also have this whole testing integration thing going on with SatLink and other SDLS implementations. So we always want to make sure that on a case-by-case basis, we can validate sat link and the other endpoint together, communicating together. But then we also have on the term, more on the implementation side, some software guidelines that we're following. So for the development of the space component, we're following ECSS software development and quality guidelines for software criticality B and lower. And additionally, we're following guidelines as well for the basically safety critical implementation itself. So we have MISRA rules, so Motor Industry Software Reliability Association guidelines, which allow us to make sure that our software is at a good level of implementation. And we have a lot of analysis, so static code analysis and dynamic analysis through tools like SonarQube and Valgrind. Does that answer your question?
Thank you.
Thank you. One more question.
Hi. How do you bootstrap your key material? Do you do this pre-launch, preloaded in a TPM, or what if something goes wrong for whatever reasons up there? Is there any way to reset? And that's possibly tricky.
That's a set of very pertinent and interesting questions. Thank you. So the process will vary from one customer to another, but basically we have in-house, we're developing tools to provision memory with a set of security associations, because it's not just keys, and keys onto the spacecraft during integration. And we are thinking about all the aspects related to the secure delivery of these aspects of the memory. It's not a solved solution just yet, but it's something we're actually working on. And additionally, you were mentioning at the end of your question, I don't think I remember the last part.
I don't either.
That's all good then? Sorry, okay, then good.
Any further questions? Okay, if not, thank you very much for another great presentation.
Thank you for your attention.